Okay.
But the micro is also the full talk.
Yeah. So I would like to. I've been kind of when I came here, I wasn't quite sure what I wanted to tell you because I didn't really have a feel for the conference. So I think I've made my peace with what I want to say. So I'll start with that. So my introduction and motivation. What's my angle today? And for the last 40 years, I wanted to make a universal digital library for mathematical knowledge. I've tried various things like higher order automated theorem proving via sorted higher order unification and so on. That was largely unsuccessful. And at some point, I basically switched my goal to what I call mathematical knowledge representation or natural mathematical knowledge management. I've been having fun there quite a while, and that's the goal there. I think that if we can get something like that going, that's going to be a critical, and I hope it's a public resource. We can all profit from it. That's what kind of keeps me awake at night. Since we're in the ProofNet, proofs are important. I'm not going to say terribly a lot with them about them. We need to certify the validity of theorems, that's kind of the foundation. They play a very big role in the modularity of things so that the math knowledge doesn't explode in size and that we can get reusability. And there's more that allow you to do. One thing I don't believe in is actually formalizing for certification of mathematical theorem. I just don't think it's worth our while. Verifying Fermat of Fermat-Last theorem gives us 0.0001 or so bit, and even if we find an error in Weil's proof, then that gives us slightly less than 1 bit of information. That doesn't motivate me at all. Having said that, formalization is wonderful because it gives us all kinds of other Teflon pans. Useful thing that I think we should be after. Right. I hope I've antagonized half of the people here. The next thing I would like to, and I do like to come out against everything that everybody is for, and this one isn't. If we look at math as it exists today, then mathematical knowledge and objects, they're transported by documents. Libraries full of them. And if you look at these documents, then most of them, depending on what you think of documents are printed. In libraries, you get their stuff on blackboards, but they tend to be ephemeral and get wiped off. Some of them are digitized. That is changed with all these retro digitization efforts. Some of them are what I think of as presentational, where you basically have not just dots on images, where you basically have text. You can actually do something with, say, presentational markup. Think of PDFs. Very few are for. Okay, even with MATLAB, Mizar, and so on, I'm guessing that's kind of 0.1% of all. And we're not gaining. There's 120,000 papers, journal articles in math alone per year, and MATLAB is growing slower than that. And then there's kind of a the thing I want to do, the semantic level, not quite formal, but what you get just to get Teflon pans going. And of course, that's around the same size, but I think that should be cut. So one of these things that this tells us, which shouldn't shock any of you, is we have to deal with what Galensalingham calls textual math, or we call math language, or so. So if we want to dominate math, we have to deal with language, and logic isn't enough. But for many things we want to do, think of I'm stuck in a proof. Is there a theorem that applies to the thing I've painstakingly constructed that gives me an upper bound of this? Wouldn't it be nice if I had a math search engine and could just basically search for something that fits? By the way, if we built such search engines, they work quite nicely, but nobody uses them. But if we could do these things, correctness is not actually the problem. Finding the stuff, accessing it, and so on, those are the problems that we need to solve, and that's where computers are good. Horizontal problems. The problem of the vertical problem of actually coming up with deep and convoluted and interesting proofs, mathematicians, or we can do quite well with our human brains. Thank you very much. One of the things, university education, that's my current favorite case study, and we have funding in this, and that's another one of the Teflon. And if we have access to the semantics of mathematical language, then we can do interesting things, help our students. So that's kind of what I'd like to convince you of. And since Stefan Schulz had this idea of contrasting logic plus and LLM plus, my take on this is that I call it a symbolic core paradigm for AI. And I would like to insist on whatever is happening here. I would like to insist that the central data structures we are working on are symbolic. We work on them via things like inference and computation and so on. And at the sensor layers and at the actuator layers, we can actually use machine learning stuff. Okay, I think that's where all of this machine learning crunchy goodness actually belongs. In the center, we need to have symbolic representations because that gives us possibility for human oversight and control. And then we can have layers that kind of do certain translations, that do the parsing for ASTs possibly more efficient than, say, the GF Haskell program. Those things I think are okay, but we need to have a symbolic core. And by the way, if we look at the human cortex, that's essentially how it is organized for many things, right? There's the lower parts of the brains. Those are machine learning, not machine learning, but very low level intuition based. But the cortex here, somehow in a way we don't really understand how symbolic. That's what I want to do. Which also with symbolic models, the thing you and me and so on, but you know, is actually building. They feed into things. Right, just to tell you about my take on this. And I think that is a much more realistic kind of architecture than the usual thing where people just say, oh, we have a problem, let's just ask an LLM to take what the LLM tells us for granted. There's an interesting discussion going on with the AI Act, which basically classifies certain tasks in risk levels, and the law, education, medicine, and a couple of others are classified as high risk. And high risk says we have loads of human accountability, transparency, explanation requirement that I can't really see the let's just ask an LLM argument will actually be able to do. If you're interested, I'll be happy to discuss that, but not this time. Okay, and since lunch is falling and I have a lot of slides and I don't know whether I will get through all of them, I'll just make the conclusions now, then we're free afterwards. So the take-home message really is, I want to convince you that there are ways of dealing with math language or textual math that are different than what all the others have done so far, right? Most of the stuff we've seen is kind of natural language understanding. Take out the trusty parser or Montague or other things, parse it into a symbolic representation, and then you have logic, and then we're happy. Or Ahmed doing it in formalization, really natural language generation. Very nice. That's another one. I don't want to do that. Especially, I don't want to do controlled natural languages, which is what Aliak has been trying to convince of us. Okay, that's also what I don't want to do. I have to basically tell you that currently doing things without LLMs, without grammars mostly, we're actually using biological periphery, which means me and my students and a couple of my colleagues to generate the symbolic representations that we need. We test this by fielding semantic support services at the moment. Yes, automation would be really nice for flexiformalization, but that is but we're not there yet. We're still in the language design, finding out what the primitives state are. I'll try to convince you of something I call flexiformalization of certain applications, incremental formalization, informalization, active documentation, those kind of things. I'll talk a bit about libraries. There's ongoing future work, which I might come back to, but you can also ask me about that. So that's the official talk. So from now on, feel free to disrupt me with questions and so on. Right, we're entering the question section. I'm going to give you a little bit of background for it. Are there any questions?
Do you mind quickly pressing camera research?
Oh, yes. Not really a question, but
you need to come back to the camera needs to catch you.
Oh, okay.
So you need to stand.
You want me to wave?
Press the button again.
Press the button again.
What's his camera actually? It's the
But it at one point focused on him.
camera will see
It's following? Good.
camera.
Okay, so there are no other questions. Let's carry
So
on.
please welcome with questions, reactions, comments. Maybe yes. Well,
I mean, so it's kind of funny, like with the CNL thing, because I'm always in this CNL corner, and I don't actually care that much about it. But for the sake of argument, let's say I'm the CNL guy. So you're talking about flexiformality. Couldn't you also do like kind of a flexi-controlled approach to language? So
yes, you could.
I know, like for some of the markup that's required currently for these annotations, there are things that I would extract automatically.
Yeah.
In our context, and you could do this without like having a full parse, but sort of like a more automatic extraction of these features.
My problem with controlled natural language is that we have more than 4 million journal papers in pure math alone. And I do not want to rewrite all of them in numbers.
Yes.
Okay,
I
so
also don't know.
even if we kind of make slaves, rewriting slaves out of all PhD students in math in the world for 10 years, we're not going to rewrite them.
But you have very cheap PhD students now in the form of language models, right? So
This is a high risk area, which means LLMs I don't trust,
right.
especially not in it. So,
I mean, from the angle of the output of LLMs and high trust, I mean, what about situations where you end up with a fully formal proof at the end, and so the only thing you need to worry about trust is the assertion, which I agree, like, involves a fair amount of trust or careful checking.
if you have fully formalized, that's exactly what I want to come against next. If you have that, bingo, wonderful, except that most people don't understand what is there, and informalization in the things I've seen of substantial kind of blows up exponentially, but no, then that's fine. If I just will not hold my breath until an LLM actually auto-formalizes any interesting research paper. It kind of, I see clever people sweating over it for months. I don't believe that an LLM can do it, but I may be wrong. I've been wrong before.
There were some.
It's just not just something I will pursue. It's wonderful if other people do these things. It's just not something I want to do. Same thing with LLMs are not the enemy. I have wonderful boxes where I can put them in now, and I want to live here. I will profit from that, right? Let my colleagues do the data cleaning and all of those kind of things here. Wonderful. The more the better. So I'm not trying, even if I'm against it, that means something for me. If I were younger, maybe I would do something in that direction. Yeah.
But maybe instead of having to write the annotations, the humans only need to check them. Something like that. Of course,
Wonderful.
it's easier to make a mistake if you like just have to press a button. You like might press it without actually.
Yeah. In the stage where I'm trying to understand what natural language, what mathematical language even is, and I don't think we know what it is yet, and why it works and why it's so efficient and effective, we have currently essentially no idea. That's my research assumption. We really don't know why it's so good, right? And until we do that, I'd rather do the work myself because it actually induces something positive in my brain. But just me. You can do it with an LLM. Wonderful. See you in Oswa.
We're new to this.
Yeah. So, what I would like to convince you of is that we kind of back off a little bit from formalization and only partially formalize a little bit more, then that would be a good thing. What we're really doing right now, if we're looking at all the documents, then all of the documents right now in the world about math are informal. Written in LaTeX, we're lucky. Word or Blackboard, if we're unlucky. And formalization is just basically a big jump enterprise. This jump is a weeks, month jump. If we wanted to make everything formal, like this distribution, then we would have big investment, big jumps. And then we would have gained a couple of 100 bytes. And yes, we have a proof. Right? Wouldn't it be much nicer if we could kind of do partial formalizations for things we feel comfortable about, certain aspects? And that would basically give us partial and stepwise formalization. And what we need for that is something, some languages, intermediate languages, in which we can express partially formalized stuff. And things like disambiguation of terms or grammatical structures and so on. Those would be, for me, partial formalization. LaTeX is a partial formalization because we write backslash section something or the other and backslash subsection. That actually makes the sectioning structure formal, machine actionable, and LaTeX actually actions on them by giving the numbers all by itself. I don't have to do it. Okay, that's what Flexiformalization is. LaTeX formalization, pretty boring, so maybe we can do something. But that's really what I think. Flexiformalization is something we really need. We need a formal format. And this is something that motivates. You basically draw the level of formality. There's a continuum of formality against the functionality you can get from services. Then you'll see that certain services kind of have different profile. For instance, something like semantic search, you need very little formality to get a lot of bang for the buck, right? In a search engine, we only need to kind of understand the structure of the formula, and then it gives you the 10 blue links, and then you can look for them. And you do not need to know whether those are actually correct or not. You can read the paper and check it before you actually use it in your research. Not a problem. So it has a very kind of a convex thing, right? Change management, right? You go to your supervisor, the supervisor says, what a nice PhD thesis, but I want you to change definition number 0.2, which means you have to go over all the 200 pages and see what depends on that definition and kind of rewrite everything. Wouldn't it be nice if your editor would tell you, oh, all the green stuff you don't have to say doesn't depend on, and here the only thing we have to know is kind of what depends on what in your thesis, and that might actually be something Flexiformalization tells you, and it might actually give you useful services. Okay. Also, not quite as convex, right? But proof search, right? Automated proof is something that's nice. You only have to kind of formalize the theorem, and then it'll do its thing or not, and then you get some kind of functionality. Proof checking is really worse than this. This is somewhat counterintuitive to most people, because you have to formalize more, maybe the proof and the theorem, and then you get some functionality. Yes, Kohlase, we have a fix. Okay? So this is something I think we should keep in mind when we look for PhD topics or our next project. I think we should bring those kind of things to less than that. So I've come up with something I call the Flexiformalist program, which is really says we should build systems not at the one degenerate end, which is logic, expressive logic and theorem, but we should kind of build a language family that allows us to do all of these things in between. And that's what I've been doing the last 50 years. And build services on top of all of these kind of convex services to test drive. I've been talking a lot about this, and my colleague Stephen Watt tried to understand what I'm doing, and so he came up with this picture. By the way, pre-DALL-E, just by image search. So this is the Flexiformal, somebody flexible. Look at this, and also formally dressed Flexiformal. Okay, so that's one thing I would like to kind of tell you as an alternative to the things we've been seeing. Okay, questions?
To back to the previous one, to the semantic search, what do you actually mean here by semantic search? So I saw that you mentioned annotating the semantics, but how exactly?
What I like is what I typically do with my colleagues nowadays. And if I'm stuck somewhere in a proof, I ask my colleagues who are much cleverer than I and say, is there anything we can do? And they say, yeah, there was this conference in Paris and there was this guy with very little hair and he did something similar. I don't remember the name. That's really what semantic search in math is, right before you start reading stuff. What we've built is things, which is formula search, where you don't remember like the energy of a signal S of t, and you kind of remember, oh yes, you have to kind of integrate over the square dt from something to something. There's probably a factor here somewhere. And would it be nice if I could just Google that? Well, actually, you cannot. Or you can Google for it, but you're not going to be very happy afterwards. Well, you can get to our trusty formula searching. You kind of make wildcards for all of these things. Actually, we're not very as well. You might want to rename them, and then this will give you, I think, well, a couple of thousand hits. All formulating, which means we're running it on the archive. We're transforming the archive from LaTeX to HTML5 with MathML, and in that, we can actually use the formula search. Quite nice. Yes.
Are there any Flexiformal services that you've encountered or imagined where either that service is not monotone or doesn't have no service with no formality and full service with formality?
No, why is this not going back in the right?
Eventually loop around.
No, because easy. I'm pressing the wrong button. Yes, this is a very idealized. This is not something experimental. This tries to give you the idea of thinking about bang for the buck. So this is
yeah. I'm just wondering, like intuitively, are there services where you sometimes lose something with creating formality? I mean, obviously, you can sort of force it to carry around the informal statements, which if you would, but you know, certain things.
Formalization in Lean uses 9.5% of the mathematicians empirically. I think when humans become involved, more formalization, unless you hide it well, is bad. I mean, all the people who who study the law do that because they never want to see math again, right? These people exist. So yes, more formalization is sometimes bad, but yeah, those are not the people I'm worrying about. I want to support my students or my kids or you all or whatever. Yes.
I have a question about the chain run.
Yeah.
What makes you think that it's so much easier than the other questions? Because I feel like often mathematicians use definitions or like subtle aspects of definitions of lemmas kind of implicitly and don't really mention it in the text. So what makes you think that you can more easily work with them?
In my SDEP system, which I may get, I have the dependence, at least the terminological dependency relation, all at my fingertips. And I can use that. We've never implemented it, so if anybody is interested in actually doing it, it's right plumb ready for the plug. Okay, so I would like to give you a little bit of a way of how do we do flexiformalization. And there's various parts of math that need to be formalized. there's the formulae themselves, the theorems, there's the kind of inheritance and modularity structure, and those I'm going to use a very simple thing. And we want to understand that there's always two kind of aspects of this. There's the presentation side, and if you think about using MathML, then we have something like a presentation tree, a layout tree, right? We have this fraction here, we kind of have two parts here, separated by a line. You can kind of have the brackets and do like a box-like or CSS box-like structures for layout. But what we're really doing, and that's what formalization recovers, is that we're dealing with application of division function to two arguments. One is the number 3, and the other one is the application of addition to a variable x or 2. Okay, so this is formal representation. This is the notation. And somehow we have to keep those in sync. Why? Because humans want to see this. They want to click on one of these boxes and get transported to semantics. Okay? So those are structures I would say, need to somehow deal with. And if you look at your system, you're probably doing some form of this. I just want to make you aware of that you're doing this. That's what it looks in MathML that allows you to do that. That's right. So we have parallel markup, we call it. You basically have two kinds of workflows. You have formalization, just go over to the formal side. Presentation, just go to the informal side if you've already have these parallel trees. But that's what you want. Now, at the next level, at the level of statements, you look at textual math, then statements are somewhat funny logical characters with funny numbers and indicators like definition or example or something like that. Right? If we go to some kind of a system like our MMT system or so, then a statement is something, by Barry Howard, you have a constant which has a type which might have a definitions or something like this. That's our way of doing it. And other systems do it basically the same way. Right? So this is what you're seeing in a textbook. The exponential function, blah, 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 blah. And really, if you want to formalize it, you're writing down something like a constant exponential. There's a type which is somehow over there, and then you have, in this case, a definite description, right? Which you can say is that. This is formal, this is informal. If you parallel markup it, then you're in business. You can kind of do formalization by hopping. Okay, isn't that nice? And if you have a formalization, then yes, you may be able to use on this informalization workshop to generate the other part. If you have a wonderful formalizer somewhere, right? You may do this. You don't have to actually write both, but you have to know what you're doing. And this is not a mapping. There are choices in there. If you're French, you write your binomial coefficients completely differently than the Americans, than the Russians, and the Arabian people from Arab countries do it completely different. Okay, so what we're doing is we're actually trying to generate these kind of things from a single source. And since most mathematicians, if they write anything at all, they're going to use LaTeX. And so we're going to use a variant of LaTeX from which we can generate this. And then have documents that kind of have both sides, and we can use that basis for systems. And if you want to pursue this further into the proofs, then if you have the well-known infinitely many primes proof, there are various ways of doing this proof, right? Lots of informal ones, different sizes of this, approaching different people, maybe a little bit of structure so that you can say in step 4 or something like this, all of those things you can do. If you want to do it completely formal, you probably want to do a lambda, right? And if you show this to my student in my AI lecture, they're going to jump from the building screaming, right? We've lost all of them. If I show them this, they may not jump, but only take the stairs running out. Okay, so wouldn't it be nice if we could kind of do something in between? And if you think about this here, wouldn't it be nice if we could kind of have these intermediate proof terms where at least the types, the thing my students want to read, that stuff here could remain informal. And have it in parallel marked up and it'll go back and forth and all of those kind of things. Wouldn't it be nice? So those are the things I want to develop. And sometimes other people help me with it. I had what we call open mathematical documents, 2006 book, and then Claudius Cohen, who's been around, actually identified this, that what Michael did is actually the lambda bar mu tilde calculus. Boy, I impressed what I had done. So that's the idea. Flexiformalization via parallel markup so that we can actually embed services into documents that make it easier to understand. That documents become much more like my PhD students, where I can, if they write something through the whiteboard and I don't understand, I just ask them, what do you mean by this? Right? What I would love to do, that my students love to do because I give it to them, our education applications, is if there's something they don't understand, they can click or they can hover. Okay, and some of the explanations are given to them. Why? Because we have annotated some of the semantics, and then I can build systems that actually generate explanations. So here's the teaching application. So what do you have to do to make this work? And the idea in this application is you want to mechanize, automatize what good teachers do. And I would claim that good teachers kind of maintain 4 fine-grained models. One model is the main model. We have to know what we're talking about as teachers. We don't even start. The second model is how to take that knowledge and formulate it in a way that my students can actually understand. What is a good example? How do I introduce something as a straw man? My slides are typically what I call the formulation model. Different from the domain, which has more information, typically all the information. And sometimes I do what is sometimes called didactic simplification for my students, or lying through your teeth. There are differences between those 2 models, which is why we typically have books and why we have slide decks when we're doing it. Very important next model is the students. When I'm teaching, I'm looking at my students, and I see when they start sleeping. I try to form a model of what they understand and what they can apply, and so on. And if I see that 50% of the people are looking very troubled, I'll try to find out and explain again, and all of those kind of things. And so there's a student competence model that we kind of need to keep track of modeling, and there's didactic models, what works and what doesn't. So that gives me a conceptual architecture, which is essentially these four models. We have the domain model, that's semantically annotated math. We have the formulation model, which is my slide deck, semantically annotated to reference the domain model. We have the learner model, which is actually only which is basically a hash from the concepts in there, the things we put into the constants in, say, MATLAB or in STF, and some way of competencies. Michael understands the concept of a plurisubharmonic to 0.6% and can apply it to 2%. And then kind of build up a virtuous cycle where if you generate active documents from your course material, you can instrument them in the generated HTML to actually phone home and say, Michael has looked at the definition of plurisubharmonic for 10 seconds, so probably the competence of remembering it went up by so and so, or has done well on a problem. And we know that applying plurisubharmonic actually is better than we thought. And that works extremely well. We're using this on 500 to 1,000 students every semester, and we get learner models, which, so for my AI course, AI1 course, we have something between 1,000 and 1,500 concepts, which means we have learner models that try to say something about all of these concepts, which we can then use to generate tailored explanations. And so at least the learner models correlate relatively nicely to the examples. That's one thing we get free if we do this. This is a bit of an excerpt of a elementary algebra domain model. What do? Well, we have these modules, bits and pieces, little pieces of concepts. And we have the member predicate. The member predicate, in this case, gives us the word member, possibly the word element. And it gives us a notation that basically says, oh, first argument, which is a list of objects. I want to say something like, I want to write down something like x comma y in S, and I write down backslash member x comma y S, which is actually the operator tree, which can be using this thing, if you think of the notation as a rewrite rule, give you automatically the presentation tree. Okay, so I have concepts for membership, I have concepts for magma, and semi-groups, and I have definitions, and those kind of things. And you write them directly in a way that are semantic. Yes, that is a shitload of work. But you get certain things for free. If you want to translate math as multilingual, then you don't have to do all of the formal part, all of the red and the black stuff, your highlighted stuff. You don't have to do it again, or at least not think about it again. And then you can actually say, oh yes, here is S abgeschlossen unter blah blah in German. So you only have to kind of do the trivial things. The other thing, right, that semi-group is called Halbgruppe, is actually somewhere here. Right? Here it's in the English semi-group, which is the system identifier, is called Halbgruppe here. That gives us vocabulary information for. And so this is a very nice, actually, turns out. Side is we can do dictionaries, glossaries, flashcards, all of these kind of things we can generate from these things. And they become extremely reusable. If you do complex numbers, you can have multiple notations for the complex unit. Some of you may know that the electrical engineers have the kind of bad practice of calling the complex unit that we call I, they call it J. If you write \imaginary unit, you can actually, in the preamble of your course, say, oh, I want to steal my colleague's stuff, but imaginary units, please use the R and not the J. And then you just specify which unit notation you want, and you can reuse your colleagues' materials. Yeah.
So, I mean, there's a lot that I like the semantic macros and everything, but of course the markup is quite heavy.
Oh.
And so the thing I kind of, the direction I wanted to go earlier with the like plexi controlled, like, so for example, the marking of which term is being defined, like the Lithuanian markup here. That could be something that like, I mean, currently I do this with like very, very naive regex type. And of course you could do something maybe slightly more sophisticated, and then you would not have to do this particular annotation, right? And of course you could probably do similar things for other types of annotation. And if you want to scale to all the documents at the archive, right, then maybe doing this kind of heavy markup is not quite feasible, but something slightly more automated, maybe.
Absolutely. And we're doing that. I'm not actually doing these kind of annotations that read, right? I'm not doing those by hand. Okay. I have tools that help me. The problem in this is when you're referring back to something like magma, you have to know what was here, which might be written by somebody else. So you do want IDEs. You do want IDEs that propose those things for you, that kind of maybe even order the right way for you. All of those things we're building and we're using, and otherwise you get you become crazy even. You tear your hair up even sooner, but you can see it's not.
But Definienda, you would always have to explicitly mark at the moment.
Typically, yeah. You can. We've had a Definienda spotter based on machine learning. It was more annoying than helpful.
Okay, well, I mean, that seems sort of surprising because it on the surface it looks easy, right?
Yeah, on the surface it looks easy. I've had a couple of students try it and all of them fail.
When was the last attempt?
3 years ago, we do have a good gold standard, by the way, right? These are human written; they're gold standard. They're actually tested on students, right, who complain all the time, and that's very helpful. Right? Yes, right now we're doing slave work, and it actually gives us the feedback of what we want. And yes, we're working on automation, and yes, we should all work on automating, making my life easier.
Is that a paper on the failure? Like, for example, on the failure from 3 years ago, is there a paper on that, or like a thesis?
There's a thesis which I'm not sure I want to look at it. Okay, but yeah, please do. You can certainly do better than that. Yeah.
So an example, like the definitions are set off clearly from the rest of the text. But,
yeah.
Does this work cleanly in mathematics settings where either like things are defined parenthetically, mid-sentence, something else, like a theorem, it looks like a theorem, or definitions there's implicit proof obligation.
Yeah, that's one of the things why we do this. And if you do this and try to mark it up and be faithful, then you'll see that you'll need an inline definition, which we call as so-and-so. Yes, or which is, by the way, unique, is an inline assertion. And all of these kind of, that's what these experiments show. And you kind of move a lot of stuff, then you actually distill the primitives. And then you see that you didn't get it right, and you kind of do it again. So we have a domain model, which kind of is bilingual mostly. 70% of the English stuff we have in German, a little bit of Chinese, a little bit, very few Turkish and Romanian, and I think one billion definition. So how do we work with this? We have this STECH, which is a pretty nifty system extension of LaTeX, the LaTeX package, and you can run it and make PDF out of it. These slides, by the way, are STECH based, and then you can expect that edit and debug what you're saying. And the first thing you do, you can also run a re-implementation of LaTeX or Rosket, which generates HTML out of this, which you can inspect and edit. But what we're getting here is not HTML only, but it's FTML, Flexiformal text markup language, which really all the stuff that we painstakingly put into the HTML, into the STF, we insert into this. Then we kind of harvest the formal part out of this into a server, which also runs the linter and the time checker if we're lucky, and those kind of things. We do all of that inside the VS Code extension IDE, and we then kind of migrate the whole thing into this learning system where our students get this. If you're interested, this talk actually you can inspect in the LES system, and then you get nice hovers and sometimes annoying errors because it's a living system. That's kind of what we do. And of course, HTML is kind of the lingua franca, and you can generate from other systems as well. We're working on a Markdown extension together with Nicolas Thierry. I don't know, 10 minutes in that direction. From PowerPoint, you can annotate, like use annotation ID, and from Microsoft Word, so that the legal reasoning people can also annotate something. Good. It's almost no time left, so not only may you ask questions, but you can also silently leave for lunch. So as long as somebody is here, I'm going to continue if the chair actually is okay with that. Okay, so one of the things that you can see here, if you look at the you're doing these definienda, and definienda are really things that have various information you need about them, right? You need a system identifier, so a concept from which we can hang, say, competency information that kind of has a URI. That's what this actually gives us in the background. And we have what we call verbalization. We have an English verbalization, which we kind of go back to the English thing. Defi name kind of makes a symbol reference, symbol name, and a verbalization that are identical. That's useful for English. For German, we have the definiendum, which gives us a pair, right? That has two different ones. And of course, Alpha has a non-standard inflection and so on. That's not something we're doing, but we're needing it, right? We have to. We're not doing the right thing there, but we hope together with Arne, we can actually do better. We're using GF to parse these things. Works quite well. So we need probably, I believe, a linguistic resource that has stuff like what's the German multilingual. What are the synonyms? In STEP, synonyms are very easy. I could say, oh, also called a Definiendum semigroup foobar. Right? That would make foobar a synonym for Halbgruppe in German. It isn't, but just for the sake of argument. Okay, so not a problem. If we have the English part, the German part, we can get dictionaries of this because any two symbols, verbalizations that share a system identifier are actually exactly the right thing. Why? Because they share the same definition. Okay, so there's a lot we can do, but most people don't want to do BSD. Okay, we have to do something here, and we have to somehow do something with the grammatical information so that Anna can also play.
So where does it say that this is German? There's sig.
The sig equals en just means for the formal part, look at the English, and the stuff I've not shown you with the file name in this case is algebra.de.tech. Or you can say in the begin document class, you can say language equals de.
If you wanted to add a language here, like you have Halbgruppe.
Yeah.
So let's say you wanted to add the Finnish.
Yes, I would just make you aware that that would be I would just copy this over. Say this is, the file is foo dot, in this case, de.tech. I would just make a foo.fi.tech and then dump it into your lab. You would basically go and say, oh, ist abgeschlossen unter, would make some finish out of that. The nice thing is the formula you never need to do anything about. The sig equals the end, the signature, the formal part, look into the English, you don't have to do anything else, right? So it's really, translation is very simple because it's all the non-mathematical part. The only place where you need to turn on your brain here, namely, what is the translation of semigroup? In Finnish, something like here, which is the SN magma, just simple name magma, right? This is already translated because I have a verbalization where here somewhere. No, there we go. There's a definition. Okay, that basically says this capital D says, oh, in German it's just capitalized. Yeah.
Also define semigroup in German.
Yes.
In the rest of the document, I just say slash semigroup and this.
No, not quite. I write backslash and curly brace
Okay,
semigroup. I could say backslash semigroup as well, but then
Yeah, but the point is that the German word is going to be copied in the rest of the document.
Yeah.
But then in several different papers, I might want to say something about semigroup.
yes,
Is there something like a library?
this is the library.
Okay. And then when I write the article, I import.
You basically say import module semigroup, and you get all the notations. You get the definition access. You get definition on cover and explanations generated, and all the whole crunchy goodness. Of course, you have to know about it, and for that we need all of those kind of things. People help me do this. What question? Oh yes, we have a couple of thousand pages of those things. So it covers quite a lot of ground. I use it in 8. I use it in 8 courses. One Teflon pan of the spin-offs, we can use this to generate a linguistic resource, like one of the language 2,265 to 400, 520 something or the other, right? All the math parts to those things. Actually, 3 of them, because and one in French, yes. So yes, you can do these things, and so the problem with the vocabulary of math, very difficult to get your hands on because it's dynamic and kind of localized, balkanized, right? It's kind of have all these little vocab islands and so on. So if you basically, we have in the ZBA math open, we have over 4 million journal papers. We assume that every journal paper only defines one concept on average. We have 4 million words with special meanings, right? I count even all the various words group, I have to count differently because they're different words. They're just homonyms, right? They look the same. But there's an upper bound of 0.5 million English words, so there must be kind of at least 10 times overloading and a non-trivial disambiguation problem, and made even more difficult because the whole thing is multilingual, that we have notation and presentations of these things. We have synonyms, we have homonyms, we have homographs, we have all kinds of things like homonops maybe. And of course we have all these kind of house styles, right? How you write your formulae is determined by your PhD supervisor typically. And you kind of do the same thing we've seen. We've seen Shravan write E and T for iota and omicron, and backwards and without an arrow. Right? I've done similar things because I learned my math from Peter Andrews, who kind of does the same thing but with iota and omicron, right? And you have all these kind of things. So we need to somehow get a control over this. Maybe only for canonical math, like your 250 languages. Maybe we do it for kindergarten to bachelor's canon, but we should have a lexical resource. So the plan really is we should fix a simple representation format so that we can generate that everybody can use. We have a problem with that. We do what Casimir does, but get our hands on everything that everyone has ever done. In this case, we have Esther. We will generate that from them. And yeah, publish that early and often. Let me give you a couple of examples. Verbs in mathematics are relatively rare, in my intuition. We have converges pointwise, divides, intersects, is, let be, we have consider, and so those are a couple of foundational things. But there isn't that much more as words go. Adjectives are much more interesting. We have the usual intersective adjectives where odd and prime, and an odd prime is just the intersection of all the odd and prime objects. We have things like simple groups and discrete topologies. Those are not intersective anymore because simple is not something you can kind of define independent of everything else without losing a lot of information. But a simple group is still a group. That's nice. That's what we call a subsective. Then you can ask yourself whether that's simple, a simple group, the same adjective as that simple group and a simple cycle the same, or even morally the same. Even if we have an example for an answer for this, other things don't have an obvious example, so you have to look at every single thing there. So there's something to be done here. Yeah.
But I think it's a very good approximation to assume that simple group is simple group in all languages. There will be exceptions, but we start with that, and then
oh yeah,
mistakes.
If you're tolerant, then that's a good default.
Yeah, but you found right from the beginning.
I agree. That's kind of a tactical decision. And then there's the scientific decision, which I'm trying to address here. But then there's also things that are partial and contravariant and so on. In these examples, those are not even subsect, because a partial function is no longer a function if you think function is a total function, right? It kind of generalizes the whole thing. The same thing with the contravariant functor is not a functor, right? So you kind of have to turn around and think hard. And when you're teaching partial functions to your students, you kind of first say partial functions, and then we have total functions that do a lot of hand waving and so on. So I think that, but those things exist. So there's interesting stuff to be done. We need to collect it. They're not obvious. That's what I'm trying to say. Yes.
I mean, like, this is just a kind of an artifact of the host language, right? Like, you could imagine a language where, like, this would be part of a single word, right? I mean,
Oh yeah.
in German, you would also say partielle Funktion, which is also an adjective, but of course, like in other languages, it might be a single noun. Right?
Yes, that makes it, that aggravates it. Romanian, I was surprised, apparently doesn't have a word for power set. Right? They say set that. At least my Romanian usually student call. And those kind of things, yes, they all exist. They make the thing hard. You need to collect that. Nouns, simple nouns, they're relatively boring. But there are less simple nouns, like Kripke structures, theorem, fundamental theorem of algebra. Those are kind of named entities. They're still boring in a way. They're just positionally non-trivial. Where it really gets interesting is functional nouns, which are really noun constructors. And we've been having a lot of fun with a general linear group of order and over the ring R. Interesting, right? And you can also say the general linear group over R of order n. All of those kind of things. You can leave certain things out, elide them, if they're clear from the context. Like the ring, you usually kind of leave out, but in the notation, you have to give it, otherwise, and nobody understands it. And then it's the natural logarithm of x, which has which you write as log x. Something interesting works here. So you need to know. You need to know somewhat. This is a functional noun. What does it subcategorize on? And that's information that you better know. Otherwise, parsing will become difficult. You have nouns for algebraic structures, like groups. And with groups, right? What is a group? It has a base set, it has an operation, it has a unit, and it has an inverse operation. Well, the last don't quite know. It's they're actually fully determined by the first one, if they exist at all. It's interesting stuff. We're using them as kind of a record structure, where we access them not by the argument order, but by successor, we say, the base set of a group. But we often also say n as the natural numbers as a semigroup, right? Oh yeah, probably plus. Or the ring of integers and those kind of, there's a lot of conversions going on here. Very interesting stuff. I'm not going to go into relations and all of that. You should have heard Philippe's talk, which did a wonderful job on this. But there's a couple of switches here. They can also have argument. We can have n-ary functions, ternary functions, seventh-ary functions. I found a sigma trivializer B, or is a sigma trivializer, or something like that. There's lots of stuff. And all of them, they're not obvious. we need to somehow collect them, make them available, curate them, I think. And so my intuition is that we should really, for the grammatical aspects, something like Jeff and Anna and my student Frederick and I already started. For the notation and argument specifiers and types and so on, we can actually use the stuff we've done in our estate-based domain models. There's lots of interesting data in Wikidata. The quality isn't terribly high, but maybe it's as a default or starter. Then we can encode the whole thing in something like JSON and then get started. Here's what we think it should look like. So you can collect. We want to in the next 1 or 2 months generate these kind of things, right? You have the argument specifiers here for defines. This is actually something that takes one argument that's an individual and another one. If there's an A, that would be a sequence argument, right? Like over there, we have typically things like for aggregated sets like X and Y in it, or A plus B plus C plus D or something like this. You have flexary arguments. You have some arguments that are binding, right? In an integral or so. We have this notion of a specifier here. We have the later binding or notation for that. We have alignments so that we know what we're talking about, say, into MathLib. And we have the GF categories that actually tell us what these things are. Okay, so that's kind of the first thing we came up on the blackboard. I'm sure this will evolve. Yeah, I would love your help. Good, and I think in the interest of lunch, I'll stop, even though people are still here. It's a lot of fun. And you're all invited to help.
Oh, please welcome.
John.
So this question is about the cost of taking a LaTeX document and converting it into STX.
Yeah.
So a lot of formalization projects like became big because they were crowdsourced in some sense. Like a lot of people were collaborating, and when you do formalization, there's also this psychological element of like you feel good that, oh, I just proved something, and there's a satisfaction, like there's a problem solving element to it. But I'm not sure, like when we semantically annotate it, a document, like is there something like which will tell, okay, I did a good job, makes sense, something like this which we can use for like crowdsourcing?
There is a lot of satisfaction you get from writing Wikipedia, right? People have done it, and we have, what is it, 35 million entries in the collected Wikipedia. So people seem to have derived satisfaction out of writing about things they care about and doing a good job on this. So I do believe that, and I feel it in myself. I sit down Sunday afternoon, kind of try to learn about functional analysis from my undergraduate or graduate, I don't even know anymore, math studies, and kind of flexiformalize the stuff. I take the Ludian book from my shelf and just do the first 15 or so. And you can see directly that I migrated
it's useful to it.
So yes, that is there. We don't have the there that but I find that a little bit fake because it doesn't have an information. We knew that there was a proof beforehand, so it's I'm not sure that motivates me so much more because math doing is not broken. Thank you very much. Right? There's two. Yes, certain things are under review, but they're also mostly not read. If we have relevant results, people will actually read them, and we'll flush out the errors. So, and for the irrelevant ones that nobody uses, it's really not a problem if they're wrong. Right, so yes, I think I see we need to develop this more. We need the Flexiformalization gummy bear that is convertible into grades or professorships, right? We still need to work on those things, but people like doing it. Especially in education, my students come and ask my colleagues and ask them, why aren't your slides self-explaining like the ones Kohlase does? That has the short-term effect of my colleagues hating me because because it's work. But yeah, so some people like it. In our we can generate things we call guided tours. Guided tours. So if you look at the definition, then if you have the definiendum markup in the begin-end definition, you have these SN, which are references to otherwise defined concepts. That gives us what we think of as the terminological dependency relation. So what I can do is I can any SN annotated word in the slides, I can actually click, and then I can say generate a guided tour for me. And the zeroth approximation of a guided tour is essentially take the system identifier, look at the downward closure of the dependency relation, subtract everything where my learner model says Shravan also already remembers it, add a couple of examples. We know those are, this is an example for a group, add a couple of quiz questions to see whether Shravan really understands, really remembers what a speaker is, and then generate little tailored to you courses. And they're not nice yet, but we know we could do. And so we need more, we need better learner models. We need thousands of more diagnostic questions, quiz questions. We need lots more examples and so on. But once we have those, and those are eminently reusable, we can actually give a very good service to our students. So for instance, another thing we do in our system is at the end of every section, in a math, you get practice problems. Now, if you think about it, those are what the author thought the average reader is. Well, I'm not the average reader. You're not the average reader, and I'm certainly not, right? So what we can do is actually, we can make your tailored practice problems that just basically kind of explore the points of pain, right? They're challenging to you without being too hard. That sometimes works, but those, all of those things we can do. And that's something that kind of gets our documents much closer to what a good colleague does when I go up to a blackboard with my colleague and they look at me and say, what does Kohlase know? Yeah, let me explain it to you. And then it's much shorter than the book they may have written. And so that's the future of scientific communication I want. And yes, it's a big thing. I feel kind of similarly challenged as Casimir does. I have all the respect for your huge project, but we have a similarly big one. But I think I know what I have to do. And if anybody wants to kind of try with the system yourselves, I'm here. I love helping people get involved. It's wonderful for doing PhD theses, by the way. It helps you think about what you're actually talking about. It's a wonderful way of procrastinating as well. Yeah. I think Philip had a question.
Yes, let's respect project B. I just wonder what is really composition and what is like prose and expression. And I would like to have your opinion on that because, for instance, a simple group, you cannot say this group G is more simple than this simple group H.
Yes, that is true.
This is a quite simple group.
No, not all adjectives have comparatives, right? That's another classification of adjectives, whether they're orderable. So not every one of them are. Right? Larger words, simpler. In math, no. I can only ask back. I mean, last night I asked you essentially the same question. What's your opinion about simple group or so? And I find myself going back and forth in my annotations. I'm currently always working with about 17,000 files. That's my corpus. Whenever something changes, I do a big rep and try to implement what I think is right now. That gives me certain data about simple groups. And I can actually look for these things and see how simple behaves. And honestly, I go back and forth between simple group as a named entity and simple as a kind of general purpose family of adjectives, which are all different.
What about lexical relations? Finite and finite. Finite type of generator, finitely generated.
Finite is an interesting example.
Function partially defined.
Yes. We see a lot of versions there, right? In a finite group, it's one of the components that's usually finite, right? Really, a finite group is a group whose kind of most conspicuous set is finite. With a commutative ring, things are not quite as easy anymore because you have two operations, right? And you don't quite know which one, but then kind of it's usually addition because for reasons, and I don't quite know what the best way of doing that is, but we have all these kind of version or inheritance things. If you're looking for a set, if you have a type mismatch, then you might actually just look for a set in the record structure there and kind of fiddle in these things. And we mathematicians, that's one of the beauties of mathematical language. We can just do it, right? Even my students who understand very little math, if I say finite group, they don't even twitch. They understand and they do the necessary thing. And our logical system can just fall over and die. Which is why I'm so much in love with math language. It's so very efficient. And the examples you gave, right? Isn't it wonderful? We should collect them. I want your slides. But yes, I don't, for the most things, the jury's still out. I hope we have a forum for discussing these things. And so that after a while, we don't talk about donkey sentences anymore, which is embarrassing because they're not math, right? Wouldn't it be much nicer if we had the decodatives challenge or those kind of things, right? Like the linguists, they have the bathroom sentence, the donkey sentences, the gangster example, the party, Barbara Party has all these kind of examples that have names. Wouldn't it be nice if we had kind of these named challenges that everybody knows that we teach to our students, and maybe some time a Schraban pops out of the woodwork and says, "Oh, I've actually solved decoded 3." So I'm very happy to get these examples. There are more.
Some more questions and concerns. Thank you very much. It's amazing how jump in there.
We have lots of problems.
It's very nice. Sorry,
What's your name? The list. Frederick Brauchi.
Yes, Andrea had the first one. Then
Apparently